Okay, so just to set some of my notation, we can go over kind of the plaintext keyword search setting that has been assumed in these prior works on searchable symmetric encryption. You have some type of email client. That's the concrete example I'll be running with. He has a bunch of emails. These are our documents, and they get uploaded to some type of storage provider. The storage provider will then index them, typically. So gather out keywords from some well-defined dictionary of keywords, and then have an index which has keyword entries and document identifiers for which emails, in this case, have that keyword appear in it. So you might think there's a typo here. That's not a typo. This is the result of keyword stemming. So typically, you don't actually just verbatim, take the, I'm going into German here, which I don't know, so that's bad. You won't take verbatim the keyword. You'll actually drop off some of the last characters. You'll make plural keywords singular, et cetera. And that'll be relevant to some of the attacks that we look at later. So now it's easy to do searches, right? You can send a keyword, say, hey, give me everything that has contract. You get back the emails / documents that have that information. OK, so we saw some very interesting and clever searchable encryption mechanisms earlier. I'm going to start actually with something that's used quite widely in practice and is much simpler. And this is called the what I'll call the Appended-PRF searchable encryption scheme. So the idea is that on the client side, you're going to first take your document and extract from it on the client side the keywords that you want to be able to search for later. And then you're simply going to run them through a pseudorandom function, or a PRF, which is just a keyed hash function. And you just append this to the plaintext. You also encrypt the email under a regular symmetric encryption scheme. And then you're done. You now have this slightly larger ciphertext with appended PRF values on the end. You can upload these to the storage provider. And the storage provider can actually do what they did before, which is generate an index, but now using these hash values will get picked up as keywords, and will, again, have the document identifiers in the table. And of course, from the email storage provider's perspective, these hash values just look like random junk. They don't have the keys. The keys are all kept on the client side. OK, so how do we do a search here? Should be pretty obvious. You take a keyword that you want to search for. You stem it if it needs to be stemmed, and you hash it under the key that you have. You get back the token, and you just search on that instead. And you'll get back the documents as before. So the great thing about this scheme is that it's what I'll call legacy compatible, which means that it works with existing plaintext storage interfaces. We didn't have to change anything about the way the server operated. We can still do this type of encrypted search. OK, I'll additionally be talking about two different types of schemes on top of that. Simple appended PRF scheme. And I won't go into too much details. The second one is actually very simple. It's just the first scheme that we just saw, except we do additionally one more thing, which is that we randomize the order of these PRF values. How can we do that? We can do it simply just by doing a sort on the output hash values before we insert it into the ciphertext and upload. And that'll become security relevant in a few moments. And then finally, there's encrypted index style schemes. I'm not going to give the details of these. We saw some talks earlier that gave a variety of ways of doing implemented encrypted indices. And I'll just kind of use encrypted index as a stand-in for something that does a better job of hiding not only the keywords under PRF values, but also encrypts the documents that they are associated with. And of course, with these schemes, the downside in general is that they are not legacy compatible anymore, which means that you do need to have server-side changes to facilitate the use of decrypting these encrypted document lists during a search. OK, so these are the three things we'll consider. The reason I picked these out is that they are actually in use in a variety of places. So this appended PRF scheme, which is perhaps the simplest you can imagine, is something that many companies are using. For example, in settings where you have a company that does encryption on behalf of enterprises before their enterprise data gets uploaded to a cloud service. So these companies like BitGlass and CipherCloud and SkyHigh, et cetera. The unordered appended PRF scheme has appeared particularly in a couple of nice systems papers that were built to do things kind of like what Mylar was doing before, but in different contexts. Particularly it's Mimesis Aegis and ShadowCrypt. And as well, probably appears in some places in practice as well, though I don't have any confirmation of that. And then finally, some of the newer encrypted index schemes that we've seen, like the Cache et al. One from 2014, are now, obviously there's been a lot of work in the literature, we're also seeing them start to appear in some contexts in industry. Particularly, I'm most familiar with this same outsourced enterprise storage to the cloud setting. So in terms of the qualitative comparison, I've already alluded to the ease of deployability issue. And indeed, we have that as you go up towards the simpler scheme, right, things are easier to deploy. You get legacy compatibility. The operations that you need to implement these are fast, right? Just running an HMAC with a key over keywords. There's definitely a lot of engineering challenges with getting these things up and running and compatible with some server API, but in general, things are easy. They're being used in practice. As you get into more complicated encrypted index mechanisms, of course, deployability goes down. And I'm not even touching on all the number of things that you can't do yet with encrypted index that things like Ugo and others have been working on, at least with the ones that are deployed in practice. Things like predicate queries and conjunctions, disjunctions that don't leak too much information. At the same time, and perhaps annoyingly, the provable security that we've seen in papers, of course, goes up kind of provably as you go down. So it's easy to come up with settings in which these schemes up in the top two are significantly less secure than the ones down here. In the most extreme example, of course, if you never make any search queries, then these things hide everything about your index. So we can prove all these nice security claims. As we saw before, there is this kind of lagging issue that is in each of these papers, and all the authors are quite familiar with it, which is the question of the fact that when we do these proofs, we prove it relative to some well-defined leakage model. And indeed, all of these schemes do leak some information about plain texts. And the question that I'm going to basically focus on in the next few minutes is just what is leaked? What is the implications of these leakage models? And this is starting to address some of the open questions that Ugo mentioned in his talk earlier. So instead of getting into formalisms, I'm just going to give some examples relative to the three schemes I described. And particularly think about this setting in which now we think of our our storage provider as adversarial. And they want to learn some information either about queries or the keywords queried or the plain text themselves from the view that they get of the stuff that's uploaded. So in the simplest case, which is this Appended-PRF case, which I have here, we can see that there's all sorts of types of things that are leaked to the adversary. Of course, from their view, these are all just random values. They can't see inside of these PRFs. They get these random values. But because PRFs are deterministic and necessarily here to allow search, we get information like co-occurrence relationships. So for example, document 1 and 7 both contain this same keyword. We get information for this Appended-PRF construction like the following, that the keyword blah came second in document 1, okay, after some other keyword. And we even see the frequency of queries that are made, right? If this particular keyword is searched for often, we get to see that as the server. Okay, so for the other two schemes, the unordered Appended-PRF scheme, the only thing that's different about this picture is that this ordering information is not leaked trivially, right? It's because these things are randomized, so it's not clear anymore that this would have been the second keyword in the plain text. For encrypted index type schemes, of course, you also don't learn that ordering information. And as I mentioned before, the leakage only occurs after queries are made, okay? So again, in the extreme case of having made no queries, the server gets no information about plain text except maybe the size of the total index. In the other extreme, which is that you query every single keyword in the document, then the leakage of encrypted index schemes, of course, develops right down to these unordered Appended-PRF schemes. And so in particular, you get these types of information about all of the documents. Okay, so we refer to this as, or attacks that take advantage of this type of leakage, as leakage-abuse attacks. Seems like a fitting name. And in fact, we don't really understand too much about the implications of leakage-abuse attacks. There's a lot of basic questions here that have only started to be answered in the literature. Obviously, the most critical question, how much does this damage confidentiality of plain text or queries? Does, in real deployments, are more complicated schemes going to achieve significantly better security than others? It could be the case that most times you query most of the keywords and you reveal most of the structure of the inverted index, and you kind of devolve back to the simpler scheme level of security. And relatedly, of course, what type of adversarial capabilities are likely to arise in practice? So we started out thinking about this a little while ago, about a year ago, and tried to understand particularly kind of the space of this last, the starting point seems to us to be the space of this last set of questions. What type of adversarial capabilities are likely to arise in practice? And so we started by enumerating a taxonomy. This is probably not complete, and of course you could get more granular in the types of capabilities or attacker goals that are of interest. But there seems to be at least two levels of attacker goals that are most important. Query recovery, so revealing which queries are being made. Plain text recovery or partial plain text recovery, learning some amount of information about plain text. For the schemes we've considered, query recovery, of course, implies some partial information recovery, but not necessarily the converse. And then we have attacker capabilities. In most areas of cryptography, we quite quickly think of the dichotomy between passive and active. Here, I think most people have been thinking implicitly of passive attacks. But it's clear, and I'll show this in a second, that active attacks in this context are going to be quite dangerous. For example, if you can send emails to the target as the malicious server. And then there's basically the question of how much side information you have about the corpus, right? Do you know, for example, all of the plain text that are stored, in which case the only thing that's relevant is which queries are being made? Say it's a public data set that got uploaded, and now you're just trying to reveal which keywords are being queried. Maybe you know some of the plain text, not others. Or you only know something about the plain text distribution, like their emails from some corporate network. So the only prior work in this space that I was aware of is this nice paper by Islam et al. In 2013. And they basically looked at one point in this space of possible adversarial settings, which is that of doing query recovery with passive adversaries when they know everything about the target plain texts. And they showed, with some attacks that I'll talk about in a moment, the ability to recover quite a number of queries in this setting. This doesn't seem to us to be the most natural setting. I mean, in particular, you have all of the plain text documents. So instead, let's roll back and actually go back to understanding what types of security attacks arise for some of these other contexts, for some of these simpler schemes. And we can really just start off with the most brain-dead simple setting, which is that of this Appended-PRF scheme, and trying to understand partial plain text recovery when we know, say, some documents. Let's say there's a public email that's kind of known to everybody, and we know which ciphertext it corresponds to. And what do we get? We get the encrypted emails themselves, but also these appended PRFs, right? And since we know the email and we know the appended PRFs and we know the keyword scheme, we can actually just say, oh, I actually know that 7813 FED is contract. It corresponds to contract. And I know that blah is file and blah blah is today, etc. So what have we learned about some unknown other encryption that's been uploaded? Well, we know right away one of the keywords is in that email. Okay, so this isn't particularly rocket science, but can turn out to be pretty damaging, at least relative to simulations that we've conducted. So we looked at the Enron email corpus, which is a kind of benchmark data set in this space. We took 30,000 emails from the employee sent email folders. We assume here, and there's a lot more in the paper, but in this, I'll just talk about one simple example, which is that, say, the adversary knows 20 random emails from this corpus, so some very small percentage. And then he just tries to run the attack I just described, matching things to what he knows. So you can get anecdotally a significant amount of information about unknown emails. So here's an unknown email, plain text. And here below is the recovered information. So it's talking about doing some contract with some company, yada, yada, getting a signature. And we can see that not all of the information you can't recover the entire plain text. In particular, there's things like these stemming truncations that we lose. But we do get quite a bit of information, right? You can see that there's something about a contract, needs to be signed. There's some documents. You even get the acronym of the company that was involved. This is just one anecdotal, visceral example of what can be leaked with this appended PRF scheme. Yeah, yeah.
Why do you only recover parts of the word? Is it because you store the text as some sort of an index?
Because, you mean for like signature?
Yeah.
Signature? I don't know how you pronounce it without the E. Signature? I think signature. No, you don't. You stem the word first typically, and then you PRF. So stemming here just means, again, like truncating off the last parts of the word, getting rid of pluralization, or you get rid of INGs often. This makes search work better. It's a common technique in the plain text setting. Okay, so that's not great. So we can think that, we should have at least randomized the hash order, and that would have made things quite a bit harder for the attacker. Because now we wouldn't trivially be able to match up on a known email the input to PRF value mapping, right? So we can randomize things. Now we're not really sure. This issue, I should say, as a side point, it's probably obvious to most of the people who've been working in this area, but actually when we look through the literature, this really seemed to be an issue that was left implicit in prior work. So in particularly these two nice papers we looked at, they actually both do this unordered appended PRF construction, but it wasn't clear whether that was purposeful or not. I presume it was. The Mimesis Aegis team, they ended up using Bloom filters, which kind of ends up randomizing, Bloom filters on the hash files, ends up randomizing them. And ShadowCrypt, the implementation randomizes their order, but the paper doesn't discuss either way what's recommended. So anyway, this is a clearly kind of subtle but important issue. Okay, so we can actually think about taking advantage of other pieces of information in this context of passive attacks to try to reveal the which keywords map to which values. But instead of doing that, let me just talk about a slightly different context, which raises another issue that I think is very important and totally understudied here, which is that of active attacks. So we're in this setting where we have an email client that's encrypting emails that they receive and uploading them after doing this keyword extraction and PRFing up to an potentially adversarial storage provider. So there's a clear threat in most such settings where you can just have the adversarial storage provider arrange to have someone else or them on some other computer send chosen messages to the victim. Whether or not this gets indexed and encrypted is kind of implementation detail. It's a little premature to assess yet because people haven't really built these schemes in deployment. But under the assumption that they do, then what happens when you get this chosen message? Well, they're going to encrypt it, they're going to do the hashing, and they're going to upload all that information up to the storage provider. And so now the adversary gets to see the result of PRFing these values. So of course, if we had just put one word in so this is, here I'm assuming the unordered PRF. So if you just had one word here, like contract, then it would be immediate that you reveal which of these two values you would get 7813 FED. If it's unordered, it's randomized. It could be two different things, right? It could be signature contract or contract signature. It's not necessarily clear which. This gave rise to an interesting game, which is the question of how many keywords can you pack into an email to try to unmask, subject to kind of not being able to infer which was which. And the idea was to try to disambiguate keywords based on their expected frequency. So if we could kind of train on other data, what is likely to be more common, contract or signature, then we get to see when we get it which one is which. And if we guessed right, then we uncover the keywords correctly. So the more keywords we can cram in, the more disambiguity we can do, the faster we can kind of reveal more and more of the code book that's underlying this keyword to PRF mapping, and therefore learn information about unknown messages. So this is just a graph looking at this disambiguation performance on the Enron training set again, where we split it up into training and testing. And we basically use the training set to do some inference of the frequency of particular keywords. So just probably too many lines on here, but just looking at the recovery rate, we can see when there's very few keywords like 2, the recovery rate's very high and our kind of error rate is very low. As you start adding more and more keywords, your recovery rate kind of goes down, your error rate goes up. The recovery rate goes down because the error rate goes up. Excuse me. But with more clever techniques, we might even be able to make this better. And in any case, the attacker can easily start sending some queries to start learning these PRF to PRF outputs. So what does that tell you in the end? That gives you some information about the plaintext that are underlying any other document, any other emails that share this PRF value with the one that you chose. Okay, and we won't know where in the email it was, but we'll know that it is in there, and so we'll get quite a bit of context information. Okay, so we have seen 2 kind of attacks against these 2 simpler schemes, the Appended-PRF mechanism, which is like, just match things up to known messages is kind of an easy way to do it. Of course, if you can do chosen email attacks, it gets even easier. Just send an email that somehow has the entire set of keywords in it, and then you're done. We saw a chosen email attack against unordered dependent PRS, where there's a little subtlety about how to disambiguate if you want to pack lots of keywords into the message. And that leaves questions about these encrypted index systems as well. Now, I should say that if we can also force chosen query attacks, then of course we can kind of do both of these chosen email and chosen query attacks against any encrypted index scheme and get back to something like number 2 and start revealing information quite rapidly. But let me instead turn to this setting which IKK looked at as the only prior work that had arose in this context, and so it's good to come clean and compare with what they did. So the IKK query recovery attack looks at the following setting, which is that the storage provider actually knows the entire email corpus. I guess this could be relevant in context where the plaintext corpus is actually public. In any case, when this happens, of course, plaintext leakage is not relevant. You know the plaintext already. But what is still potentially hidden by encrypted search is which queries are being made against the server. So it's not trivial to figure that out. So you get a sequence of queries on various keywords. We can just kind of assume, as they do, keywords are uniformly selected from the set of all keywords. And you get back the documents, et cetera. The adversary's goal is to figure out which keywords are being queried when. So they detail this very computationally expensive attack that kind of uses simulated annealing to solve this NP-complete problem that ends up being sufficient to reveal queries. Instead of going through that attack in detail, let me just point out that there's a much simpler attack that you can do in this context, which is to simply look at first the number of documents that are returned. And if you know all of the plain text, then you can also figure out yourself, like how many documents are going to be returned by each individual keyword. Okay? And with that knowledge, you can simply say, oh, if it's a unique number of documents if the number of documents that were returned is only returned for contract, like contract's the only keyword that returns 2 documents, then you're actually done. You already know what that keyword was. And if there is some ambiguity, then you can start using more coincidence relationships, co-occurrence relationships across different documents to help narrow down the set of possibilities. It's really very simple. And it's very fast, so you don't need to try and solve any NP-complete problems or whatever. You just kind of do some counting in a for loop, and it works quite well. So here's a comparison of the query recovery count attack, what we call the count attack. Yes?
So why weren't they doing this simulated annealing business? Because they wanted to come at least in the worst case, as opposed to, so your attack seems like it sort of makes distributional assumptions, right?
It makes what?
Distributional assumptions, right?
More than that, you know the whole plain text, which is corpus, which is the same as the IKK setting. So we're pointing out that in the IKK setting, you can do something much simpler than they did. Why did they do it? I'm not really sure. I think partly they actually use less information than we do in our attack, in the sense that they kind of ignore the fact that they know how much counts are coming back. And I don't know if they knew they were doing that implicit or not, but in any case, And I'll mention what relaxing the assumptions in a second.
Well, I guess they said could they also then study how their algorithm would do after noise was added?
Right.
In this case, if you add noise, it sort of makes this attack trivial.
No. I mean, it depends on what type of noise you add. We looked in the paper at doing the obvious thing, which is like padding out the counts of documents. That has significant performance implications, but does eventually erode the attack capability, but it takes quite a bit of padding. They look at a particular noise model that's very strange. They look at only noising the co-occurrence relationship across keywords, and it was this like error model, and we didn't look at that any further. It doesn't seem like it's something people are going to use anyway.
Okay, but if you add noise, you're going to have to do some kind of distribution on it, right? You won't just be able to match.
Absolutely, yeah. So in the paper, I don't have slides on it, but in the paper we look at what happens, for example, if you don't know the entire data set, but you only know some fraction of the documents, right? And how the attack degrades. The IKK attack degrades much worse than the count attack, actually. But both of them degrade pretty quickly, like at 60% of the corpus. If you know 60% of the corpus, you're still not getting a huge recovery rate, something like 0.2 for the count attack and less for IKK. That seems like the most important thing to measure to me right away, because this is a very strong assumption to know the entire plaintext corpus. But there's lots of open questions. We certainly didn't look at all potential countermeasures or even all potential settings that could be interesting here. Great questions. Other questions? Cool. Okay, so I'm actually just going to wrap up on that part and just say there's a few things that that are important here. One is that the little details matter, right? So for these in-practice schemes that people are using, doing something as simple as ordering or not ordering the PRFs that are appended to ciphertext can make a big difference for security. And this seemed implicit, even though in hindsight it's kind of obvious. And two, there's just this huge set of questions that we have still, right? We only, in this talk and in the paper, there's only a few other settings we looked at beyond the ones described here. But there's this huge scope of potential adversarial settings that we need to worry about. And for each of these, we actually need to do empirical analyses to understand in a real deployment scenario what is going to be abusable about this leakage. We haven't even gone into the question of more complicated leakage models like some of the newer schemes have than just co-occurrence information. So anyway, there's lots of open questions. The takeaway is I think there needs to be, provable security only gets us so far in this context. You really need to do empirical analyses. And that's not to say that provable security is not important. Of course, that gets us to the place where we can just focus on the leakage. But at that point, there's lots of open questions. Any other quick questions about this before I move on to machine learning? Cool. Perfectly clear. All right. So let's switch gears. We're going to put searchable encryption to the side for a moment, at least for 30 minutes until the next talk, and then it'll come back. And instead, let's talk a bit about machine learning. So machine learning systems in my world, and for the purpose of this talk, are going to be this kind of supervised machine learning setting where you get some labeled training data, database of data. And then you run one of whatever many potential favorites machine learning training algorithms that you have to generate a model F from this data. Whereas this model, it's a function that takes as input a vector of features and outputs a class label or a regression value or something of that form. And then we go ahead and deploy this F in some application to profit from the awesomeness of machine learning. So ML, in case you have been under a rock for the last few years, is super hot right now. We're back in one of these machine learning summers or springs. And we're seeing a huge uptick in the number of places where machine learning is used. Not only in medical applications for personalized medicine based on people's genetic information, but more classic applications like facial recognition. And as well as even nowadays seeing these machine learning as a service systems that allow people to upload their data to Google or Amazon or one of these other startups like BigML. They'll do the heavy lifting of training for you at your command, and then they'll expose a model that you can access for predictions over the web. So this resurgence suggests that we need to think very carefully, particularly about privacy when databases of data are using sensitive information. And there's, of course, been a lot of work on privacy of data over the many years. This is a miserly subset of the data, of the prior work. But we know at this point that at least we should be very careful with releasing sensitive data. Like this database, if it has like medical data in it, we need to think very hard before we release that data, even in some type of de-identified form. And so I think there's a clear takeaway there, and there's been lots of interesting work both on finding attacks as well as understanding countermeasures. So for purposes of talk, we're going to assume a model in which the database of data is not going to be accessible to attackers in the wild. This does leave the question, though, of what happens when you get access to just this machine learning model F, which is, after all, something that's trained from the sensitive data, so it's a function of it. And this is going to be our concern. What happens when you get access to this model F? What types of bad things can happen for privacy? As far as I'm aware, there's only been one prior work that, but I'd love to hear about others if you know of them, that has looked at this question. And Attanase et al. In 2013 showed how if you get the ability to download F in some very specific case studies that they looked at, then you can infer one bit of information about the database, like whether it was lots of Indian-speaking people or not Indian-speaking people was one of the examples they had. So we'd like to do a bit more than this. And in particular, we've been exploring this attack thing that we call model inversion. Yeah. Fair enough. Beyond learning F, they use F to infer one bit of, basically a predicate over the database, a different predicate over the database. So the definitions I don't want to go into, but you have to read the paper to get the definitions. On top of knowing F, they learn one extra bit of information, yeah. I mean, explicitly, they're looking at things like trying to figure out what the ratio of training set items were for like different language speakers in a language prediction application, or a voice recognition application, or whether a particular type of trace data was in a training data set for a network intrusion detection system. And F in those cases varies, so it could be something like an SVM, a support vector machine, so it's like a set of linear coefficients for defining a hyperplane in the feature space. They also looked at hidden Markov models and other things. So it's a very interesting paper, but pretty preliminary. And we're going to look at a slightly different kind of attack model than what they looked at, which is this idea of model inversion. And we're basically going to look at a sequence of examples, case studies of what we call model inversion attacks, and it should hopefully become clear what I mean by model inversion through the course of these examples. In context personalized medicine, where we look at the ability of an attacker to try to use a machine learning model F that's been trained on patient data to predict their genotypes, all the way to things like neural networks for facial recognition, where we use a model F to try and recover recognizable images of people's faces. And then, if I have time, I'll just leave off with a very preliminary discussion of potential countermeasures. And this is really just mostly questions, not any answers. So we'll start with this context of personalized medicine, which is where we got our start on this idea of model inversion. And in particular, we were looking at what's called pharmacogenetics, which is the idea that doctors can take advantage of outcomes data generated during research studies that has information about people's like demographics, their health history, their genetic markers, and also their outcomes under treatment to help train a machine learning model to predict how best to treat future patients. And we in particular partnered up with some people who were involved in this International Warfarin Pharmacogenetic Consortium study. That's the name of the author set, is IWPC. Where they showed that you can basically generate a linear regression-based classifier, so something pretty simple that does a good job of predicting the initial dose of warfarin given some genetic information and other health history information, demographic information about a patient. Warfarin is an anticoagulant. It's used to like prevent strokes, and it's been notoriously tricky. It's notoriously tricky to dose. So if you ever had to take warfarin, you have to like go back to the doctor every 2 days to get it titrated, because too much warfarin means you'll have uncontrolled bleeding events. Too little warfarin means you will you'll still get blood clots and have problems. So it's been a target of this pharmacogenetic research literature for quite a while. So the other thing that was helpful to us is the data set in this case is actually publicly available because they got informed consent signatures from all of the patients. I was actually surprised when I found that out. So that means it's good standing because we can simulate attacks with it, and it seems just like the types of data sets that should be remaining private.
So you mean genetic markers, phenotypes?
Mm-hmm. You can download it. Yeah, so it's a good stand-in for an attack in our context, yeah.
To clarify, when it says predicts initial dose of warfarin, you mean predicts the correct dose of warfarin?
No, the initial dose of warfarin. So in the regimes that they're suggesting for use, you will, they're just limiting attention to trying to predict the starting dosage. In the current clinical practice, you get 10 milligrams of warfarin the first time your doctor decides you should go on warfarin, and then you go back in every 2 days. They're trying to replace that 10 milligrams with a prediction based on your genetic markers and other information. And the hope is that those first 2 days, which are quite the riskiest, I think, for negative effects, you'll do better. So you'll be in the right range for warfarin for your body sooner than you would otherwise. Yeah, it's crazy tricky. Like, don't eat broccoli when you're on warfarin because it messes up your INR and stuff. It's something I learned. Okay, so good. So yeah, and not only is the data public, but also perhaps more directly relevant to our story here is that the machine learning model is available, right? So you can just go to warfarindosing.org, and if you happen to know all this information, or more particularly if you're a doctor who gets this information in the course of treating a patient, you can make use of this linear regression model. It's also published in all the papers. Okay, so we looked at this, and some of our colleagues who are interested in genetic privacy said the most interesting privacy issue they thought of in this context is whether having access to F gives some information about people's genotypes. And so in particular, we wanted to figure out whether we can build an attacker that takes some other partial information about a person, like their demographic information, health history, something related to their suggested initial dose of warfarin, like their final stable dose after titration, which happens several days later, and maybe you read it off a pill bottle. And from that information, F, predict what their genetic markers are. So we refer to this as model inversion because of the idea that you're kind of inverting the model to try and figure out an unknown feature from your point of view. And so in particular, it's an algorithm that not only gets F, but has some information on these other features, the known features, some information, again, on something related to the output Y prime, as well as the model F. Yes?
Isn't F like a proprietary algorithm?
No, it's on this web page. Yeah, it's hard to read because it's got lots of stuff on it. No, so F in this case is a linear model, so it's literally a linear function. So the coefficients of this AX plus B for more than one dimension, those coefficients are published in the paper. They're on this web page underneath the hood, obviously. This is for collecting the features. You click a button and it runs the model. So it's definitely public. And most often for medical settings, for research, they do publish the models, right? The point is to make it available for people to use. In other contexts, it may be proprietary. And then there's this nice question of whether like black box access to it would provide yield fruit, and it will here, but we can talk about that in a second.
Isn't those more sensitive than the genotype itself? Because genotype does not give you like, it's just like 2 genes, right? You just know this, but I mean, those ones like more sensitive.
So the linear regression itself is more sensitive than...
What I mean is the dosage, right? Because you use the dosage to differ genotype. So is it like you are using more sensitive data to differ less sensitive data, or?
I mean, I guess if you don't have access to the person's dose, then yes, that could be one way to look at it. I mean, there's actually 2 questions there. Like, one is how damaging is it to learn these genetic markers in the first place, and that's something that we don't really understand, and we in like the global sense, right? Right now we know these genetic markers are very well correlated with warfarin sensitivity based on lots of work. Whether they're correlated with other information that people would consider privacy is like, to be determined, I guess. So for right now, it may not be the scariest thing. And then two, the question is like, how do you get this other side information that you need? And that's really context dependent, so it'll depend. If you know someone's initial dose of warfarin because you asked them or whatever, and don't know their warfarin, their genetic marker, then you can start using this attack. And we'll see other examples of model inversion attacks for other settings as well. Great questions. Okay, so right, we want to build a model inversion algorithm that, does that, target person's genotype. So I'm not going to go into the details and try and give you a high-level idea of what this does. It's actually relatively simple, and it's black box. It actually doesn't take advantage of the particular structure of F. Intuitively, all you do is you enumerate all possible values of this genetic marker, this unknown value. And for simplicity, I'll just assume we know all the other features, though it's easy to extend. So you get all these potential feature vectors. You run them forward through the model, okay, to get the outputs. And then you basically, intuitively, if there wasn't any error, you'd kind of be done. You could just figure out which y value matches the known y value. The y value you have is not exactly the output of this model, so it's actually got some noise and error into it. In this case, then, what we'll do is just output the value of the genetic marker that maximizes the likelihood of it being the correct one, given all the information we do know, which is the F outputs, as well as the probability error models, which I didn't mention, but there's something that's also available with these linear regression models. So ignoring the complicated math, what all this says is just like, give me the genetic marker that maximizes the likelihood of being correct, given all the information I have. And this is a pretty standard maximum a posteriori estimator from the machine learning kind of world. And it's optimal in some well-defined sense that I won't get into. Okay, so that was a quick rush. Let me just tell you what the result is. That this is a comparison of guessing one of the two genetic markers, VKORC1, which I have no idea what that stands for comparing basically improvement over baseline guessing. The baseline guessing is like 36% accuracy. This is like 1 of 6 values. And here is the setting I was just talking about, this adversary A, our model inversion, which gets access to model F and knows everything except the genetic marker. And he gets this big speed up or improvement over baseline guessing. For comparison purposes, I graphed also on this how well you'd be able to predict this if you had access to the original trained data and trained a linear regression directly to predict people's genetic markers given the other information. And so what we can see is that we're doing almost as well as if you could have trained on the data set directly as the attacker. So this model F has quite a bit of information, in hindsight, perhaps no surprise, about this relationship between these other inputs and the genetic marker. Yes?
You don't use only the model, you use also the output, right?
We assume that you don't know the output, you know something correlated with the output. You know like their stable dose of warfarin. Yeah, if you knew the output, you would just invert the linear function.
You know the stable dose as opposed to the initial dose? Is that it?
You know the stable dose as opposed to the initial dose, exactly. So, sorry that wasn't clear, but the initial dose is what's predicted by the model. Then you still go through titration process, which changes that dosing that you actually get. And so what you really get is like the output plus some error, which is the error of the model, actually, which is why we can do it. Okay, so that's one example. How much time do I have? 15 minutes. Interesting.
So can I ask again?
Yeah.
So you're sure that all the leakage comes from knowing the model as opposed to maybe it all came from this stable? Like what is the damning part of sensitive information? Maybe it's just the dosage that he receives, and is that like your linear regression didn't matter at all? I mean, I don't know.
That's a great question. We didn't actually do that particular analysis of like what happens if you just try to predict given the stable dose. We did look at like how the performance degrades as you know less and less of the other information, like the health history and the demographic information. And definitely it goes down, right? As you start reducing information. But knowing I don't think it would work that well because there is correlation with the other values, right? That's the reason they kept it in the original linear regression, the other health history and other information. But doing a full like teasing apart the principal component analysis of we didn't do that. So it's a great question. Yes?
Can you explain the threat model again? Like why would people tell others their stable dosage? Like where does the attacker get this information?
We're assuming that you get access to it. So you can read it off their pill bottle. You can, I don't know, Mission Impossible, like go in through the window and like read the bottle. It's a little bit contrived. I agree. The pharmacist knows. Other people know. The pharmacist won't necessarily know your value of VKRC1. Like doing an exhaustive investigation of like when would this be practical or not is an open question. I don't know if it's worth pursuing. There's probably other genetic our colleagues were very interested in, like what about breast cancer and all these other, there's like tons of pharmacogenetic research out there. It might be more interesting to look at other ones as well, where there's actually a compelling privacy issue, immediate privacy issue with learning the genetic marker. Yeah. This is just the one we had ability to do analysis on. Yeah?
This sounds similar, like when people talk about that in differential privacy, there's that law about smoking causes cancer, and that's like if you want to
Smoking does cause cancer. Don't smoke.
Yeah, if you want to have like something that has such strong privacy, it's basically impossible. Like this sounds like one of these cases where smoking causes cancer.
I think, yeah, so that's a good, so differential privacy is one model. I could talk about that later in more detail. There's a question of like whether this is just taking advantage of population statistics, like population-wide statistics. This does work better on training set members than on non-training set members. In fact, this is training set member data. So if you know someone was in the training set, you can do a little bit better in your inference. More generally, I think from my point of view and also talking to the doctors, it wasn't clear to me a priori that you could do this at all, right? Given just the model, which is a set of linear regressions that's meant to go forward that you could actually do this model inversion and learn unexpected information. So if you're thinking of the doctors and saying, hey, should I release this linear regression model? It's like, well, you need to know the genetic information to use it, so that's the privacy important thing, whatever, it's fine to release. It wasn't clear. Now you would say, oh, well, actually, no, you learn all these other correlations that were not meant to be used with the model in the first place. So, yeah. Let me keep going, and we'll come back to that if we have time. Okay, so we started looking around for other places where model inversion causes problems, and I'll just very quickly now, because I only have 10 minutes, go through a couple more examples. So the first is from these machine learning as a service settings. So this is a screenshot of this very nice website, BigML, that has a gallery of machine learning models that other people have uploaded. They have a nice interface. You can kind of set models to be black box or white box. White box means anyone can download the model. Black box means you can only make predictions against the model. In fact, you can ask BigML to charge other people to make predictions against your model. So it seems like an interesting potential business model, not to overuse that term here. Yeah, anyway, pay for predictions. So in looking around this site, we saw that there actually are quite a few models that seem potentially privacy sensitive. So I'll just tell you about one of them, this 538 stake survey. This is from 538, is this Nate Silver blog. He got famous for predicting elections in the US a while ago. And they had this blog post about trying to get a sense of like whether how you like your steak prepared is correlated with risky lifestyle choices. I guess under the slightly ridiculous assumption that people who like their steak rare, I say ridiculous because I like my steak rare, are more likely to have done things like cheated on their significant other or gamble or have, I guess, a low income is considered risky. I don't know. So, which guilty as charged. So anyway, no privacy up here. So anyway, they have this decision tree model that basically takes as input this information, outputs this prediction of whether you like your steak rare or not. And they were doing this in the course of this study. So we asked the question of like, oh, okay, here there's clearly like some more sensitive than other pieces of information here, right? And can you use model inversion to predict this information given some other information? Like here, you just ask your buddy if they like their steak rare or not, and maybe you know these other pieces of information. They may not be willing to tell you that they've cheated on the significant other, and we're going to try to figure that out. Again, because we didn't realize this at first, but we realized the de-identified training data set is actually available online, which allows us to evaluate ground truth. So another good simulation for attacks. The de-identified training data set is available online. And in fact, if we didn't have this, we wouldn't be able to evaluate how effective our attacks were.
So there's a list of people without a name that says whether they're cheated.
Yep. Mm-hmm. Yep.
How they likely to stay.
Yes. Yes. So if you did a SurveyMonkey survey like a few years ago that happened to ask you a lot about your marital infidelity as well as steak preferences, you are probably online in this data set. Yeah. Sorry for the bearer of bad news. Not only are you, well, okay. Anyway, so we can kind of just, I'm going to speed up a little bit here. We can do a map estimator just like the one we did before. It looks a little bit different because it's a decision tree and the types of error information we get is different, but this is all within the white box model or black box model of Big ML. And we get like okay accuracy. So baseline guessing for infidelity is quite high, right? Because most people report that they have not cheated on their spouse. But our MI attack does do a little bit better. We also went back and looked a little bit more carefully at Big ML. We realized actually there's a bunch of information on the interface that we weren't taking advantage of. In fact, information about how many instances in this training data set, which again, these simulations we assume we don't have, but the interface tells us how many of those instances match certain paths in the decision tree. This helps us build a slightly better model inversion attack adversary that does better accuracy, but also does spectacularly well on precision. So for members, so for people who reported themselves as having cheated on their wife, we will, or husband, we will catch that, at least via these suggested by these simulations. Okay, so that's another example, and very much the same kind of kin as the linear regression. There's some small nominal valued unknown, a binary value with the cheating, or some like 1 out of 6 values for the genetic marker. We also want to look at settings that were much different, and particularly look at neural networks for facial recognition, where here the unknown is actually going to be the entire input of the machine learning model. And let me just use 4 minutes or something to go through this. Okay, so here we are doing facial recognition. This is a well-understood task. You have a bunch of pictures of each person. I only showed one picture of each person, but you typically have a bunch of pictures of each person. You feed that into your database, and you train a machine learning model to try to later get an image and predict whether or not this person is, or figure out which of the people this person is or other. And so we looked particularly at a bunch of neural network-based mechanisms. These are admittedly simpler than the ones you'll see in production use right now. Like Facebook has this deep face thing, which is this like 10-layer deep neural network thing that requires significant amounts of Facebook scale information to train. We're looking at like kind of circa early 2000s neural network mechanisms, but it seemed like a good place to start. And so what is the neural network? It's actually just a description of a function, mostly linear functions with some nonlinear activation, yada yadas. Won't get into too much jargon. But the point is it's a function that takes in pixel data and outputs a prediction of which class label you are, as well as typically confidence information about how confident the prediction is in which person it's predicting. So we asked the question of, can we just do model inversion completely? Like say you're given access to this machine learning model F, not access to the database, but just the machine learning model F, you have no other information except the labels maybe, the people, of people, and you want to figure out recover a recognizable image of the person. Okay, so here we digging in a little bit. We have this function F. This is the neural network. That's pixel data. It's totally unknown to us which one is the right one for each of these labels. We actually get back a vector in these cases of confidences, so real valued like 0, 1 confidences of which person this, or how confident they are that this person is any one of these people. And you just take the max of these confidences as your class label. Of course, here we have a much different kind of thing, right? We have a huge space of potential things to search. So those kind of algorithms we looked at before that were doing maximum a posteriori estimates won't work. You'd have to go over a large number. That's not going to work. We realized, though, that you can take advantage of a typical tool in the machine learning trade, which is that you can cast this as an optimization problem and do efficient search over this space. And particularly because of the situation when you have an interface that outputs this real valued class information. This confidence value is a kind of rich source of information for us. It can tell us well, what we can do is then say, here, find me the x1 to xn with the highest confidence for Bob. That means highest confidence for this y sub Bob. Because this is a differentiable function, kind of by design, these neural networks, we can compute gradients and figure out at any given location which direction should we go to try and get closer to the most confident value of Bob. So to compute gradients for the gradient descent, we can do it white box, we can do it symbolically using any library that does gradient computations. With black box, you would need to do numerical estimation, meaning you would actually like query the oracle on nearby points and see which direction you're going with the confidence. We haven't done black box attacks. We've only looked at white box in detail. The softmax is so fast, though, that, and the number of queries would be low enough that you could actually do it, I think, black box over the network, but we haven't actually done the implementation. For the other ones, it seems it would be prohibitive right now because they're more complicated and it would take a lot more queries. But anyway, it's fast in the white box setting when you have access to the model locally and can do symbolic calculations. So here's some examples, which are probably hard to see on the quality of the screen, of doing this type of attack on the 3 different models. So you have some target, and then you run this optimization on softmax, and you get a picture like this. It's should be hopefully recognizable out there. These other ones, you definitely are noisier, but there's still some recognizable features in the various relevant to the target. And this was all trained on this and tested on AT&T data set. I mean, we split out test images and stuff, but it was using the AT&T data set. So we wanted to know, like, for some of these, it's pretty clear that it's recognizable. It leaks a lot of information about about a training set person. Other ones, it's not quite as clear. So we did this recognizability experiment on Amazon Mechanical Turk, in which we basically asked, like, if people could re-identify members of the training set given this image that was output by the model inversion. So we just asked them to click on the person in the lineup that corresponds to the altered image, and we have a bunch of controls and stuff as well. Is there a question? Or just a stretch? Okay, good. Right, and so there's a bunch of details in the paper, like overall average accuracy was like 80%. And there are some people who are like surprisingly good at this. They were able to re-identify like 95% of the time. Skilled workers, just people who were consistently good at doing this. And it's amazing to me that they can do that for these kind of noisier pictures, but pretty impressive. Okay, so I don't have time, unfortunately, to go over countermeasures, which is, I guess, just the way I like it. So no one likes anything that actually makes the world better. Okay, and actually, I mean, just the high-level bit on countermeasures is like we need them, right? In the sense that if you believe that these things are potentially dangerous, then there's a lot of cool questions to ask about how to prevent these types of attacks. And I guess I'll just leave it at that because I think I'm out of time. No, I have more time, so I should fill it like gas. Yeah, well, I think I'll just leave it there and actually take more questions. Yeah, thanks. Yeah.
Do we have any sense of utility privacy trade-off for these models?
Utility privacy trade-off for these models. And these models, you mean the machine learning models?
Yeah, if we add some noise, take away.
Yeah, so I think mostly no. We did do some work in the Warfarin paper to understand whether differential privacy would help. Kind of is the go-to choice these days because it's such an interesting framework. And there, it's a little bit misaligned, right? Because differential privacy says that like the model won't change too much whether or not a particular person is in the database or not. That said, the attacks work better on training set data, people from the training set, so we thought, oh, that's actually kind of symptomatic of differential privacy style problems. And two, if differential privacy did, help in kind of an ad hoc sense, even though it wasn't designed for this model inversion resistance, then we get 2 birds with 1 stone. You get differential privacy plus some resistance to this type of model inversion attack. So we did look at that. But unfortunately, at least for the state-of-the-art mechanisms we looked at the time, there's this problem that like, to get the model inversion not to work, you kind of had to add so much noise that you caused problems with the utility. So in this context, for that particular setting, there seemed to be no solution for a utility privacy trade-off. That said, there could be better mechanisms, or one could find something not differential private that would just speak to model inversion and perhaps do better. Yeah?
Isn't it unfair to criticize different like these techniques, because this is kind of like learning like smoking causes cancer, and like these papers like.
Well, let's be clear here. I'm not criticizing differential privacy.
It's saying that like those techniques don't work here, right?
Yeah.
Like the first paper, like Don's first paper says that this is not what differential privacy is meant for. Like this is what she called it's not privacy.
Well, I mean, I think she would be happy if differential privacy found more applications than what she originally intended. As I said, it's a little bit misaligned, right? But our intuition was that the type of noise you get added will reduce model inversion success. And in fact, that's true, right? Like, as you get into lower epsilons, the risk of disclosure in the model inversion goes down significantly. So it does help, but it hurts utility. We're not trying to malign differential privacy. We're just saying if you happen to try to use differential privacy here, you're not going to get too far. Even actually, if you forget model inversion, you try to use differential privacy here just for the sake of differential privacy, it's not going to work in this setting where utility is very high. So more research is needed.
So I think we should take the rest offline.
Sure. Yeah.
Since there's collective setting. Let's take Tommy and Alice.
Thanks.